Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So today we're going to continue on the lecture for sinusoid and phasor. So today we're going to discuss on the impedance admittance. So before this, we already discussed on introduction, sinusoid, phasor, and also the phasor relationship for circuit elements. So in this class, we're going to discuss both these two topics. So what is impedance? Impedance Z of a circuit is the ratio of a phasor voltage V to the phasor current I measured in ohm. And what is admittance? Admittance is Y is the reciprocal of impedance measured in Siemens. So basically this is the equation where Z impedance is equal to V over I. So in our case, in complex number, so Z impedance is equal to R, the real part, plus Jx, the imaginary, or in phasor form, ZV. And the admittance is the reciprocal of impedance. So basically Y is equal to 1 over Z. So that these three elements we need to consider in the in our topic, in our class after this, R, L, and C. So the impedance of R is basically is equal to R. If it's L, inductance is equal to JWL. L is the value of inductance, and C, the capacitance, is impedance is equal to 1 over JWC, and the admittance Y is reciprocal of the impedance. So you need to remember about these facts. So if it's inductance in DC circuit, it is short circuit, while in high frequency, which is AC circuit, it is open circuit. However, as for capacitor, in DC circuit is basically an open circuit. The capacitor will be an open circuit, while at AC circuit, the capacitor will represent as a short circuit. So you need to remember this. Don't confuse about on short or open circuit for L and C. Okay, let's look into this example. So for this question, we have to find VT and IT. So VT is the voltage across the capacitor over here, and IT is the current going through the circuit. So in the circuit, there's a voltage source, 10 cos 40, and we have two elements over here, resistor and also a capacitor. So similar like DC circuit analysis, we need to find the current flowing to this circuit first. Then you can get the value of voltage over here, V over here. So what we need to do first? So the first thing, you change the voltage source from time domain representation to phasor domain representation. So you get Vs equal to 10 with 0 degree phasor. And after that, we need to find the total impedance of the circuit. So the total impedance means that we need to add up the resistor value over here and also the capacitor value over here. So that's why we get 5 plus 1 over JWC. So the capacitor, if we look back at this table over here, capacitor, the impedance is equal to 1 over JWC. That's why you get this equation in this equation. So C is the value of the capacitor, W is the angular frequency of the voltage source, 4. So W is 4 over here. So you just add up these two values and you get 5 minus J 2.5 ohm. So J here, because it's 1 over J, that's why you get minus J over here. So hence, the total current that going through in the circuit is I equal to Vs over the total impedance of the circuit, Z over here. So you insert these two value in the equation and you get this value at the end, 1.6 plus J 0.8 ampere. So after that, you already know the current, total current passing through the circuit. Then you can get the voltage across the capacitor using this equation. It's just a simple equation, V equal to IR. However, for AC circuit analysis, R is changed to impedance. So in this case, we need to find the voltage across the capacitor. That's why we put this ZC, the impedance of the capacitor. So we know Z of the capacitor is 1 over JWC. So that's why I is divided by JWC. So you insert all the numbers over here, and finally you can get the value of the phasor, the voltage of this value. So basically you can just use calculator to divide or multiply this equation or this number. So after that, we need to find the VT and IT. So for example, V, we get a phasor form, so you just change it to the time domain form representation. So 4.4 cos 40, 4 is the angular width of the voltage source minus the phasor value over here. So for the next question, you can do it first before the tutorial. So I will also discuss this question in the tutorial tomorrow. So this is the answer. You can check after you did the question. The last topic of this in this chapter is impedance combination. So in this topic, you're going to learn on the series and parallel impedance combination and also star delta circuit transformation. So let's look into the impedance combination first. So if you look at the circuit, this is basically a series of impedance Z1, Z2 until Zn with a voltage source. So the thing that I want to highlight is the total of Z, the total impedance of the circuit in series. So basically is the addition of all the element in the circuit. So Z1 plus Z2 plus ... plus Zn, similar like this circuit. And also for the voltage, if the total voltage in the circuit in the closed loop is basically V1 plus V2 plus until Vn, like this. So this is the voltage divider that I want to show you. So if you have a two element over here, Z1 and Z2, and you have a voltage source, and the question asks you to find, for example, V2. So V2 is equal to Z2 over Z1 plus Z2 times V, the voltage source. Similar goes to the Z1. If the question asks you to find V1, so V1 is equal to Z1, the impedance of Z1 over Z1 plus Z2 times V, the voltage over here. So this is called voltage divider. I think you already know and already discussed in detail in the DC circuit analysis in electrical principle 1. So let's look into the parallel connection. So why it is called parallel? Because all the element is in parallel. Z1, Z2 until Zn is in parallel with the current source also. So from here we know that the total current flowing here is equal to I1 plus I2 until plus In. Okay, and the total impedance of the circuit is basically 1 over Z EQ. EQ is the total impedance. This one Z EQ. 1 over Z EQ equal to 1 over Z1 plus 1 over Z2 plus 1 over Zn. So for the parallel connection, you can use the current divider. So I1, for example, you need to find the I1, where the source is a total current here. We know the total current over here. So I1 is equal to Z2 divided by Z1 plus Z2 times the total current I. While I2 over here, if the equation asks you about to get the I2, is equal to Z1 divided by Z1 plus Z2 times with the total current over here. Okay, so the Z here is cross each other. So I2, the upper value here is Z1, not Z2, different from the voltage divider. So let's look into the star to delta transformation. So this circuit is to delta to V and V to delta transformation. So V or Y here is over here. This is Y. And delta is the triangle over here. So we can change from this kind of circuit, a triangle circuit, to a Y-shaped circuit or V-shaped V circuit. So this is basically important where to what we call to simplify our circuit analysis. So how do we change from delta to V or from V to delta? Okay, so this is conversion from V to delta. So you need to remember this equation. For example, Z1. So Z1 is over here from V to delta. So this, for example, the equation give you Z1, Z2, and Z3, and you need to change it to a delta form to simplify your circuit. So to get Z1 over here, we need to use this equation. ZA, not Z1, ZA over here. We need to use this equation. So ZA is equal to Z1 times Z2 plus Z2 times Z3 plus Z3 times Z1 over Z1. So you need to remember that if you need to find ZA over here, the equation should divide Z by divide or by Z1. So Z1 is under the equation, under over here. Similar to ZB, the division is to Z2. So if you want to find ZB, so the division is over Z2. Similar to ZC cross to Z3. So you need to remember this. Then the upper side of for these three equations is the same. So Z1 times Z2 plus Z2 times Z3 plus Z3 times Z1. Similar to find other value for impedance A, B, and C. Okay, so you have to remember what actually the impedance that you need to divide. Okay, hope you understand. And how about for the equation for delta to V conversion? So from delta here, you want to convert it to Y circuit over here. So you have to use this equation. So for this equation, if you look at these three equation, you will find that the lower part here, ZA plus ZB plus ZC is the same, similar to Z1, Z2 and Z3. So the difference is the upper part, ZB, ZC, ZC, ZA, ZA, ZB. So the tips is, if you look at here, for example, Z1, you want to find Z1. So basically, the upper part is basically on the left, on the right, and also the right part element. So basically, Z1 is equal to ZC times ZB divided by total of addition of ZA, ZB, and ZC. So I hope that you understand how to remember the tips to remember the equation. And also you need to know that a delta or V circuit is said to be balanced if it has equal impedance in all three branches. So Z delta is equal to 3 Z V. If it's balanced, the impedance is similar for the three branches. Okay, let's look into this example 9.10. So find the input impedance of circuit in figure 9.23. Assume that the circuit operates at W or angular frequency equal to 50 radian per second. So we have a circuit here, over here, and the question asks to find the input impedance, which is from this here. So similar as the DC analysis circuit, this is DC circuit analysis. If you look at these two elements, this is in series, this is in series, and to solve the total impedance from this part here. So basically these two and these two is parallel each other. So you need to solve this first, then you can add up with this element here, because this is actually, if you parallel these two, this element here is in series with the total of these two parallel. So let's look into how we're going to solve this. So the first thing that you need to do is to add up the series element, which is the inductor here and also the resistor, and also the resistor and the inductors over here. So for this example, we separate it with Z1, Z2 and Z3. So Z1 is the capacitor over here, Z2 is the 3 ohm and also the capacitor 10 millifarad, Z3 is the inductant and the resistant over here. So Z1, we can use the equation 1 over JWC. So we get this value. And Z2 is over here. Let me draw it a bit. So Z2 is here, and Z3 is here. So I hope you understand. So Z2 and Z3. So the total, we just add it up. 3 plus 1 over JWC. C is the value of 10 millifarad. And Z3 is equal to 8. 8 over here, resistor plus JWL. So L is the value of the inductance over here. So once you get the total, you can use this equation to get the Z in or Z total. So basically Z2, which is here, is parallel to this part, and after you did the equation, adding these two up in parallel, we just add the Z1 over here. So that's why we get this equation. And the Z in basically is equal to 3. Z in is equal to 3.22 minus J 11.07 ohm. Sorry, my drawing board is not sensitive, very sensitive right now. I'm not sure what's the problem is, but it's okay. Hope you understand. So for this, I think it's this similar equation. Okay, let's look another example in V delta transformation or star delta transformation. So if you look at this circuit, you might not see where is the delta or where is V circuit, but if you look it carefully over here, this is from this point here. It's basically like this. It's a delta circuit over here. So this is A, and over here he basically is C. So the element at this part here is basically 2 minus J for ohm, and over here we have another element J4, which is this, and over here is 8, which is this one. So basically it represents a delta circuit over here. So to make it easier to analyze this circuit, because for this question it asks the question asks to find the current I over here. So if we simplify this circuit, we can get a easier or simpler solution to easier technique to simplify, easier solution to simplify the circuit. So I hope you can see this delta shape over here and the element over here. So if we convert it or do the conversion delta to V, so we get this circuit like this. This is a Y shape. It's like a Y shape or T shape, right? So V circuit over here. So if you look at this, it's much easier to analyze, because why? Because these 3 elements here is basically in series. This is in series, so we can edit these two up, and also once we add this and this together, we can do the parallel between this circuit and also this element over here. So it will be simplified as a one loop circuit. So once we get a one loop circuit, so we can just simply use V equal to I Isaac. So we have a total of Z impedance of the circuit. We have a voltage, so we can get the current flowing into through the circuit, which is this current value over here. So this is how you find the impedance of the V circuit, ZAN, BN, and CN, like this one. So from this delta, we convert it to V. And then we find the total of the impedance from this point, basically. So that's why we get this equation, and the total is 13.64 with a degree of 4.204 degree ohm. So we have V voltage and also the impedance, the total impedance value, so we can get the current. So this is the value of the current. So I hope you understand. We will do more question and also discuss the answer in the tutorial tomorrow. So I hope you attend the tutorial. So we're going to do it through Google Meets. Okay, that's all for the lecture today, and also for the chapter, our first chapter in electrical principle 2. So I hope you understand. If you have any question, just WhatsApp me. So thank you, and Assalamualaikum.